So imagine that we have a machine just like that man has, and we have a string tied to it, and we have the string anchored on the other side. And we turn it on and we increase the frequency. At some special magical frequency, we're going to see this occur, where the two ends of the string are not moving at all, and we have maximum amplitude right in the middle. And it seems to be just wagging around back and forth right there. That is the first standing wave pattern that emerges. We call it the fundamental. It emerges at the lowest frequency. The harmonic frequency here will depend on the substance. It depends on the string, how tight it is, what it's made from, how long it is. It may even depend on it depends on the density of the substance, things like that. But every substance has a frequency at which it will vibrate with a standing wave pattern, with the fundamental standing wave pattern. What defines the fundamental standing wave is that it has one antinode. Remember what an antinode is. The antinode is the point where there's maximum displacement away from the equilibrium position. So this has 1, 2 nodes and one antinode. Same thing over here. Here's another depiction of it. There's a node, there's a node. Remember what node means? It means that there's no motion at all. That's completely destructive interference. And then right here would be the antinode. So the fundamental standing wave pattern has one antinode, 2 nodes. It occurs at a special frequency. We call that the first harmonic, or the fundamental frequency. And we denote it with a little subscript 1, so F1. Let's imagine that we crank our machine up, we tell it to vibrate our string with a higher frequency. This standing wave pattern will collapse. It's going to look kind of chaotic. And then once we reach a new special frequency, all of a sudden we're going to have a new standing wave pattern emerge. It's going to look like this. We refer to this as the second harmonic. The second harmonic has, do you know what I'm about to say? How many antinodes does it have? Well, here's an antinode. Here's an antinode. It has 2 antinodes. And it has 1, 2, 3 nodes. Are you seeing a pattern? Yeah. The harmonic corresponds to how many antinodes there are in the system. The first harmonic has 1 antinode. The second harmonic has 2 antinodes. Again, here's another picture over here. Here's an antinode. Here's an antinode. 2 antinodes. What about the third harmonic? It's going to have 1, 2, 3 antinodes. So the number of the harmonic corresponds to how many antinodes there are in the standing wave pattern. There's another relationship that you need to know, and it's given right here. The frequency of that standing wave pattern is equal to the wave pattern multiplied by the fundamental frequency. Let me give you an example of what I mean by this. Let's say that the frequency at which this first harmonic occurred. Now remember, what is frequency? Frequency is how many waves pass by every single second. So how many oscillations there are per second. The unit is hertz. Let's say that this occurred at 150 hertz. So I call it the F1. It is the frequency at which the fundamental standing wave pattern emerges. What would F2 be? Well, very simply, F2 is 2 times the fundamental. So in this case, it would be 2 times 150. It would be 300. So if I crank my machine up to 300 hertz, I'm going to get the second standing wave pattern, the second harmonic. What would I have to program my machine? With what frequency would I have to program my machine to get the third harmonic? Yeah, use this equation. The third harmonic is going to occur at 3 times the fundamental frequency. The fundamental was 150. This is just an example. So the third harmonic will occur at 450 hertz. And how is the third harmonic pattern defined? It has 1, 2, 3 antinodes. How many nodes does it have? 1, 2, 3, 4. The number of antinodes will always correspond to the number of the harmonic, and the number of nodes will always be 1 greater. So this has 3 antinodes, it's the third harmonic, but it has 4 nodes. Could you predict at what frequency the sixth harmonic would occur? Remember, my fundamental frequency was 150. So at what frequency will the sixth pattern, the sixth harmonic occur? By the way, could you guess that this was the sixth harmonic pattern without me telling you? What would you have to do? You'd have to count the number of antinodes, right? There's an antinode. 1, 2, 3, 4, 5, 6. Aha, it has 6 antinodes, therefore it's the sixth harmonic. How many nodes would it have? Just one more, 7. 1, 2, 3, 4, 5, 6, 7 nodes. So if I want to know the frequency at which the sixth harmonic standing wave pattern occurs, what am I going to have to program my machine to do? It's very simply going to be 6, that's the n in this equation, times the fundamental, that's the F1, times 150. And that's going to equal 900 hertz. There's also an equation that you need to know for the wavelength. So when I go to calculate the wavelengths of the harmonics, I need to start by thinking about the second harmonic. The second harmonic is defined by having 2 antinodes, right? That's what we said earlier. And therefore, the second harmonic is composed entirely of one complete wave. It goes down, up, and back, right? That's what we said earlier with one complete wave cycle. So when I think about the wavelength of the wavelength of the second harmonic is equal to the length of the string. So the wavelength of the harmonic is equal to L, the length of the string, because the second harmonic is one complete wave cycle, down, up, and back, right? Well, let's think about the first harmonic. In the first harmonic, do I have a complete wave? No, I just have one antinode. I just have a peak. I don't have a corresponding trough and back. This is half of a wave cycle. So the wavelength would be twice the length of the string. The wavelength of the first harmonic is 2L. Therefore, we could say that the length of the string, just rearranging this, the length of the string is equal to the wavelength over 2. That's what these equations mean. So once again, the first harmonic, the equation for the wavelength of that wave pattern is 2 times the length of the string, because the length of the string is just half a wave. Here, the length of the string is a full wave, so the length is going to equal the wavelength. 2L over 2 is another way of putting it. You're going to see a pattern emerge. Here, in the third harmonic, how do I know this is a third harmonic, besides the fact that it tells you? How could I determine that? Count the antinodes, right? 1, 2, 3 antinodes, so I know it's the third harmonic. Well, how many waves do I have? I have 1 and a half. In other words, I have 3 halves waves. So the length of the string is going to equal 3 times the wavelength over 2, or we can say that the wavelength equals 2 times the length of the string over 3. Why is that? Because I have a complete wave, and then I have half of a wave. So the wavelength is going to be 2/3. If I were to divide this into thirds, here would be 1/3, 2/3. The wavelength is going to be 2/3 the overall length of the string. The length of my wave, remember the wave is defined as one complete up, down, and back cycle. So here's a complete wave, and it's 2/3 of the total length. Again, you can rearrange the equation and say that the length of the string is equal to 3/2 the wavelength. In the fourth harmonic, I have 1, 2, 3, 4 antinodes, 5 nodes, and you can see that I have 2 complete waves. Down, up, back, there's a complete wave. Down, up, back, there's a complete wave. So the wavelength, the length of the wave, is very simply half of the length of the string. Or you could say that the length of the string is equal to twice the wavelength. These are equations to help relate the length of the wave to the length of the string? The length of the wave, how does it relate to the length of the medium, the string in which the standing wave has emerged? A general form of this, which is very easy to remember, is that the wavelength of any harmonic, the first harmonic, the second harmonic, the third, is going to be equal to, do you know what it is? Twice the length of the string over n, where n is the number of the harmonic. Look, this is 2L over 1. This is 2L over 2. The third harmonic wavelength is 2L over 3. The fourth harmonic wavelength is 2L over 4, and so on and so forth. You can see that all of my even-numbered harmonics are going to involve complete wave cycles. There's one complete wave cycle. In the fourth harmonic, there are two complete wave cycles. However, all the odd-numbered harmonics in this case are going to involve fractional wave cycles. This only has half a wave cycle. This has 1.5 wave cycle. And that's what these equations are getting at. The length of the string equals the wavelength over 2. The length of the string is half a wave. The length of the string is 3/2 of a wave. However, my even-numbered harmonics, the length of the string is a whole wave, or the length of the string is 2 whole waves, etc., etc. This is the form of the equation that I think is probably easiest for you to know and remember. The wavelength of any harmonic standing wave pattern is equal to 2 times the length of the string over the number of the harmonic. Let me now summarize that for you with some equations. The equations you need to know for harmonics. First of all, you need to know that the number of antinodes is going to be equal to n, where n is the number of the harmonic. And it's always a whole number. N equals 1, n equals 2, n equals 3. The first harmonic, aka the fundamental, the second harmonic, the third. Let me give you one more little reminder. The first harmonic is always going to look like this. So the number of antinodes is going to equal the number of the harmonic, the first, the second, the third, the fourth, and so on. The frequency of that harmonic is going to equal n times the fundamental. If this, for example, occurs at a frequency of 100 hertz, this is going to occur at a frequency of 200 hertz. This would occur at a frequency of 300 hertz. This one would occur at 4 times the fundamental. The frequency of the fourth harmonic is going to equal 4 times 100, 400 hertz. I think that makes pretty good sense. The wavelength of the wave at that harmonic standing wave pattern, 2L over n, where once again n is the number of the harmonic. Does that make sense for this first standing wave pattern? Yeah, it does. This is only half of a wave. So the length of the whole wave would be twice the length of the string, 2L over 1. Here I have a whole wave. So the wavelength is just the length of the string. 2L over 2 is L, and so on and so forth. These are the equations you need to know for harmonics, and you need to know what harmonics are. They are special standing wave patterns that emerge at specific frequencies. Remember what a standing wave is? It is the result of constructive and destructive interference in a wave system due to multiple waves, a wave coming and a wave being reflected back. What's reflection? What's interference? Etc., etc. Things that you need to know. And you can apply them all to analyze harmonics, which, as it so happens, is the basis for all music, which I think is pretty dang cool. And we will talk about music and sound in our next